first order reaction. The first order reaction, A goes to product P. The rate law is written as rate is equal to K into concentration of A to power 1. But any number to power 1 is the same number, so don't need to put power 1. How can we tell that a reaction is a first order? Is after carrying out the reaction, we plot a graph of concentration of A against time. We plot a graph of concentration of A against time t, then we get a graph of that shape. When you get a graph of this shape, then we can tell that the reaction is a first order with respect to A. Or when you plot a graph of rate against time t, we get a straight line. This is rate, or 1 over t against time. When we get a straight line, we deduce that the reaction is a first order with respect to A. Secondly, we can express the rate as negative dA. This is equal to K into concentration of A. When we correct like terms, we can say that negative dA over concentration of A will be equal to K dt. If we integrate both sides, integration of 1 over A dA will give us natural log A. This will be equal to Kt plus C. How do we get the constant C? We let T is equal to 0. Therefore, negative natural log A naught is equal to C, because K times 0 is 0. Where A naught is equal to initial concentration of A. Substituting for C, you can see that negative natural log A is equal to Kt minus natural log A naught, where A naught is the initial concentration of A. Correcting like terms, we can see that natural log A naught minus natural log A will be equal to Kt. This is called integrated rate law. Similarly, when you plot a graph of natural log A against t, we get a straight line where the slope or gradient is equal to negative K. When we extrapolate this graph to 0, this is 0, then we get natural log A naught. But natural log A is the same as 2.303 log A. So when you plot log A against t, we get a straight line. This time the slope or the gradient is equal to negative K over 2.303. Then when we extrapolate to 0 degrees, then this is 2.303 log A naught. The intercept will be 2.03 log A naught. Subtraction of log means division. When you put log of A naught over A against T and we get a straight line, we deduce that the reaction is a first order reaction. In summary, a first order reaction can be identified from the following graphs. If we plot a graph of concentration of A against time and we get that shape of the graph, we conclude that the reaction is first order. The rate is proportional to concentration. Or when you plot a graph of rate against time and you get a straight line, again we conclude that the reaction is the first order. Here slope is equal to K. Or when you plot a graph of natural log A against natural concentration of A against T and you get a straight line, again we conclude that the reaction is a first order. We conclude that the reaction is a first order. Or when you plot a graph of low concentration of A against T, we get a straight line. Then we conclude that the reaction is a first order. In this case, the slope is negative K over 2.303. So when you are given the values and you get these shapes of graphs after plotting the following quantities, then you conclude that the reaction is the first order with respect to A. Half-life is the time taken for the concentration of a reactant to reduce to a half its initial concentration. Then half-life of first order reaction. From the integrated rate law, where we have A naught over A concentration, natural log or initial concentration over A is equal to K T at T is equal to T a half, which is the half-life. Then A is equal to A naught over 2. When we substitute, natural log A naught over A naught over 2 is equal to K T a half. Then we can conclude that natural log of 2 will be equal to K T a half. Then T a half is equal to natural log of 2 over K. So when you are given K, you can find half-life of a first order reaction, or when you are given a half-life of a first order reaction, we can get K. In this expression, there is no component of concentration, so we can say that a half-life of a first order reaction is independent of the concentration of the reactant. So when you plot a graph of concentration of A against T, we said you get a hyperbola. We can get a half-life from this graph by finding a time for a concentration is C, and then we find the time taken for C to reduce to a half. So the time here is a half-life. But you have said that if we have got a half-life, we can get the rate constant K for the reaction. The following examples will illustrate the first order reaction. Example 1. The data in the table below was obtained for the reaction 2A is equal to a product A. Plot a graph of log A against time. B. From the graph, determine the order of the reaction. C. Calculate 1. The rate constant for the reaction. 2. Half-life for the reaction. Your graph should have a shape like this. Make sure it has got a title. A graph of log concentration A against T. The vertical axis is labeled log to base 10 concentration A, and the horizontal axis is labeled time in hours. The graph should be a straight line with a negative gradient. From the shape of the graph, the reaction is a first order reaction because the rate is proportional to the concentration of the reactant A. See part 1, the rate constant is the negative slope. And see part 2, the half-life is the natural log 2 over the rate constant. Example 2. A. State what is made by the term 1. Radioactivity. 2. Half-life. B. Below the table shows the data for radioactivity decay of an element Z. 1. Plot a graph of activity against time. 2. Determine the value of a half-life of the element Z. 3. Determine the decay constant and state its units. Radioactivity is the emission of ionizing radiations or particles by spontaneous disintegration of atomic nuclei. Half-life of a reactant is the term taken by its concentration reduced to a half of its initial value. Remember to put a title and axis labels. Get half-life by extrapolating the graph to 12.5 counts per minute. To get 41 minutes, the time taken for the concentration to fall from 25 to 12.5 counts per minute. 12.5 counts per minute is a half 25 counts per minute. Decay constant K is equal to natural log 2 over half-life is equal to natural log 2 over 41 minutes, which is equal to 0.17 per minute. Example film. The table below shows kinetic data for the reaction bromide plus bromate in acidic media. 1. Plot a graph of 1 over T against the volume of bromate 5. 2. Determine the order of reaction with respect to bromate 5 and give a reason for your answer. 3. Determine the rate constant for the reaction and state its units. 4. Write the equation for the rate of reaction in terms of concentration of bromate 5 ions. Before plotting, calculate 1 over T and fill it in the table below. Part 1, the graph looks like this one. Remember to put a title, label the vertical and the horizontal axis. Considering the shape of the graph, the rate is proportional to the concentration of bromide ions. Therefore, the reaction is a first order with respect to the concentration of bromide ions. Part 3, the rate constant K is equal to a slope which is equal to 0.054 minus 0.00 over 10 minus 0 equal to 0.0054 per centimeter cubed per second. Part 4, since the reaction is a first order with respect to the concentration of bromide ions, the rate law is expressed as rate is equal to K into the concentration of bromide ions. Zero order reaction. For zero order reaction, the rate law, rate is equal to K into concentration of A to power 0, or rate is equal to K. A plot of a graph of concentration of A against T will give you a straight line. When you plot a graph of concentration of A against T and you get a straight line, then that reaction is a zero order. An experiment to show that reaction of iodine with propanol in the presence of an acid is a zero order reaction with respect to iodine solution. 1. A given volume of iodine is added to a given volume of propanol. 2. Mixture, a specified volume of sulfuric acid is added, and immediately a clock is started. At specified intervals of time, say every 10 minutes, a given portion of the mixture is pipetted into a conical flask containing sodium hydrogen carbonate to stop the reaction. The amount of iodine remaining is titrated with standard sodium thiosulfate solution, and the moles of iodine remaining are calculated. Then when you plot the amount of iodine remaining in a given portion of the mixture against the time, we get a straight line showing that the reaction of iodine with propanol in the presence of an acid is a zero order with respect to the concentration of iodine solution. Factors affecting the rate of reaction, they include temperature, concentration, pressure, and 4, a catalyst. Effect of temperature on the rate of reaction. When the temperature is increased, the rate of reaction increases, because 1, increase in temperature increases the kinetic energy of the particles, which increases the rate of collision. When a reaction to take place, particles must collide. So the higher the rate of collision, the higher the chances of reaction. 22, increase in temperature increases the fractions of particles with energy higher or equal to activation energy. Activation energy is the minimum energy required by the reactant to react. After collision has taken place, the reactants must have a minimum energy called activation energy to enable them react. So 2, increase in temperature increases the fractions of particles with energy equal to or higher than activation energy. A plot below shows distribution of molecular kinetic energies at different temperatures. The shaded area shows the fraction of molecules with energy higher than the activation energy. Note that at higher temperature, the fraction of molecules with energy higher than activation energy is higher than the fraction of molecules with energy higher than activation energy at a lower temperature. Energy diagrams to illustrate activation energy. Exothermic reaction. In exothermic reaction, the products have got lower energy than the reactants. The energy required for the reactant to form activation complex is what we call activation energy. In endothermic reaction, the products have got more energy than the reactants. The energy required by the reactant to form activated complex is called activation energy. And the activated complex is energy-rich species in a reaction that can either form products or reactants. The species with the highest amount of energy in a reaction is called activated complex. Activated complex can either break to form products or reactants. Molecularity of a reaction is the number of species required to form activated complex, or the number of species involved in the rate determining step. Molecularity is usually 1 or 2, but rarely 3 or above, because the probability for simultaneous collision of 3 species is almost negligible. 2. The second factor that affects the rate of reaction is concentration. The higher the concentration, the higher the rate of reaction due to increased frequency of collision. So when the particles are concentrated, the rate of collision is higher than when the particles are less concentrated. 3. Pressure. The higher the pressure, the higher the rate of collision, which increases the rate of reaction. A catalyst increases the rate of reaction by lowering activation energy. When you draw energy diagram of catalyzed and non-catalyzed reaction, it will look like this. Note that the activation energy of a catalyzed reaction is lower than activation energy of uncatalyzed reaction. Omutima kwe guteeterera, azalibwa bakungu, yakuzibwa bulungi, atambula bulungi, oba kiriba kitya ng'ono nsula naye, nga tulya naye, oba muyaga gutya oba buzibu butya ono tufa naye.
ono yabasinga
wenjagala n'omutima gwange gwegusibye
yono yono
wenjagala n'omutima gwange gwegusibye
yeye yeye
wenjagala n'omutima gwange gwegusibye
omutima kweguteeterera
wenjagala n'omutima gwange gwegusibye
bulamu kwebutambulira oba butiti butya oba kwaka gutya ono ndifa naye
gwegusibye
era ndiba naye